Cloud gaming is a huge application and is gaining in popularity, but it's also very challenging from a technical perspective. Gamers want big screens with lots of detail and fast frame rates, but also sub-frame latency and the ability to play on phones, tablets, and other devices on 3G, 4G, and 5G connections. In this article, Jan discusses three approaches to region of interest encoding that may soon be used to improve the cloud gaming experience while lowering bandwidth requirements. Hi, Jan. I have a question for you. You are saying here, region of interest encoding can enhance video quality while reducing bandwidth. Wait, what? Enhance video quality while reducing bandwidth? That sounds like an oxymoron or like a miracle. Can you explain?
Yeah, I mean, basically what region of interest encoding does is it devotes more bits to the regions that your eyes are focusing on. So in the context of a game, for example, you care about what your opponent looks like, you care about what the, how many bullets you have left or other aspects of your defense or your offense, but you may not care about the background that's at the peripheral of the frame. So what typical encoding does is it encodes every bit of that frame the same way. It applies one bit rate to the entire frame. Region of interest encoding will identify the important regions in the frame and add more bits to those frames to the detriment of regions that you're not focusing on. So you reduce bandwidth, but you increase the viewer experience because they don't care what regions they're not looking at look like.
Why is region of interest encoding particularly relevant to cloud gaming?
It's particularly relevant to cloud gaming because it's a very challenging encoding environment. So the typical cloud gamer, they want 4K screens, they want 60 frames per second, they want sub-frame latency, and they want to be able to play on a 3G or 4G connection. So really, if you're watching a 4K movie on your living room television set, you can devote 25 or 50 megabits per second to get really, really good quality over the, every frame in the movie. On the other hand, if you're trying to play a game on an iPad that's connected via 3G or 4G, then you really need to get the bit rate down. And the only way to do that effectively in a gaming environment is to use region of interest encoding. And looking at the typical game, there's a lot of fine detail. It's computer generated, so artifacts are very easy to spot where they might not be in traditional, regular video. So challenging content, challenging playback environment really makes it challenging for compression companies like NETINT to supply the encoding at a very high quality and at low bit rates.
You are listing three approaches to region of interest encoding. Can you explain the main differences and also the basic assumptions of which those methodologies are based? So first is CAVE, which stands for Content-Aware Video Encoding.
So CAVE is a technology that relies on metadata from the game vendor. So the game vendor decides which regions in the frame are important to the gamer, sends that metadata to the encoder, and then the encoder performs the region of interest encoding. So the big assumption there is that the game vendor will provide the metadata that you need to run the region of interest encoding.
And then we have gaze tracking.
So gaze tracking relies on a device connected to your computer that actually tracks where your eyes are looking. So you've got this device detecting where your eyes are looking, and that's transmitted back to the cloud gaming platform, and then the region of interest is applied. So the key assumptions there is that you have a gaze tracker. Now, the authors of the study that I cite in the article are very aware that not everybody has gaze trackers. They're trying to make it work with webcams, and if they can do that, then you've got a general purpose device that everybody will have that can perform that type of region of interest encoding, but not enough people have gaze trackers for that to be effective.
And the last one is deep game based on machine learning.
So deep game has two aspects and both related to machine learning. Number one, you have to train the game beforehand on the encoder so that the encoder via artificial intelligence can understand where the region of interests are. And then on the encoding side, when you're actually rendering the game, you've got to apply that. So there's a machine learning application side on the actual encoding that you have to perform to make that work.
The cave approach should be most accurate in identifying region of interest encoding, but requires metadata from game developers. The gaze tracker approach can work with any game, but requires hardware that many gamers don't have and is unproven for webcams. Deep game can work with any game, but requires pre-game training and involves in-game running on reference models. None of the three proposals described seem to have progressed towards implementation, even though all appear to be very viable for improving quality of experience, reducing bandwidth and latency, while working with existing codecs and encoders. How does NETINT product support region of interest encoding? Is that something that is an inherent part of our video processing units and transcoders?
Good question. There's two answers. So the T408 does not have an artificial intelligence engine on it. And what you can do with region of interest encoding there is you can do it manually using the FFmpeg region of interest filter. So that's pretty much like what we're talking about. You get the metadata from the game and then you apply it once you know what the regions of interest are. And there's limited applicability. I mean, you could apply it to the middle, 50% of the video and degrade the quality on the edges, but there's nothing intelligent there. You have to upload those coordinates beforehand, and while they could be specific to a game, they're not going to be very easily modifiable, and it's not going to be responsive to the game itself. So that's what you can do with FFmpeg, and you can do that with any FFmpeg encoder. What the Quadra has is, because it's got an artificial engine on it and the ability to run the artificial engine during encoding, is we have what's called facial recognition. And this doesn't help for gaming as much, but if you're shooting a conferencing video or a surveillance video and you want to prioritize the quality of the face, you can apply some models that we have and that we've worked on and work with Quadra so that the facial regions are prioritized and they look better to the degradation of other regions. And there's an article I wrote on that perhaps we can put in the show notes. And there's also an application note that relates to Quadra that tells you how to do that.